Okay, let's continue our discussion on different flip-flops and uh, we continue by an example for timing diagram of JK flip-flop. So we want to complete the timing diagram for JK flip-flop. Okay, so in timing diagram, some information are given and we are supposed to determine the output and the next state of flip-flop. Let's assume we have this clock cycle. So the clock cycle is a signal like this. Okay, and let's say we have output y with the initial value of 0, and it's always useful to show the edges by dashed line. If the JK flip-flop or any synchronized device is high active or rising edge sensitive, we should like dashed lines rising edges. If there are falling edge sensitive, we need to determine or mark the falling edges. So here, because the device is rising edge sensitive, we mark the rising edges. And then we have our input output y and two inputs j and k. Inputs j and k are given to us and we are supposed to determine the output. So j becomes 1 at this moment and then goes back to 0 for 2 clock cycles, then changes to 1 and changes to 0 and it remains 0 until the end of the cycles. K input starts from 0, it's 0 for 2 cycles and it changes to 1 for 3 cycles and 0 and again 1. And this one is K input. So the values, of course, we know are 0, 1, 0, 0, 1, 0, 0, and also 0, 0, 1, 1, 1, 0, 1. Okay, we want to determine the output. We should notice that Q of t plus 1, the next state, is determined by the value of Qt. And before completing the table, so here it's like q of t plus 1 and here is q of t. And before completing this timing diagram, let's see the characteristic table for JK flip-flop. We have J and K and Q of t plus 1, 0, 0, 0, 1, 1, 0, 1, 1. We know that if there are 0, 0, Q of t plus 1 is Q of t. If the inputs are J0, K1, the output is 0. If J is 1, K is 0, the output is 1. And if both inputs are 1, the output will be complemented. So let's just complete this timing table using this characteristic table. Let's do that. The first thing we do, for determine Q of t plus 1 in cycle 1, cycle 2, cycle 3, cycle 4, 5, 6, and 7. In cycle 1, we should look to Q of t uh, j and k for q of t. So j and k both are 0. 0, 0 means q of t plus 1 is equal to q of t. Because q of t is 0 at this moment, q of t plus 1 will remain 0. The next step, in order to determine the value of output, I'm trying to show it with my highlighter, but it's not working. Okay, that's fine. In order to determine the value of q of t for this cycle, we should look to values of jk in the previous stage. So j is 1, k is 0. If j is 1, k is 0, it means set. So the output should be equal to 1. So we change the output to 1. Next state, for cycle 3, we look to j and k. J is 0, k is 1, it means reset. So the output goes to 0. For cycle 4, we look to cycle 3 values of j and k. J is 0, k is 1, again means reset, so the output is 0. For cycle 5, we look to cycle 4. Cycle 4 has j equal to 1, k is equal to 1, it means complement. So what is the value of q is 0, so it will be complemented to 1. The next cycle, cycle 6, we look to cycle 5. J and k are 0, it means no change. And finally, cycle 7, we look to cycle 6. J is 0, k is 1, it means reset. And so this one is the timing diagram of JK flip-flop. Okay, so let me just show it with some arrows. So we see that these values determines this output. These values determines this output. These values determines this output. These values determine this output. These values determine this output. These values determine this output, and these values determine this output. Okay. Now that we learned how to draw a timing diagram for different flip-flops, so here we had JK flip-flop, so we can do the same thing for T flip-flop, D flip-flop, and other different type of sequential circuits. I'm going to discuss something called propagation delay. So effect of propagation delay. What is the propagation delay? Let's assume we have a gate, okay, gate and gate. And one of the inputs are connected to logic 1, and the other input is connected to input D data, and here we have output. We know that if both inputs of, let's say in initial state, the input is 0. We know that in in the AND gate, the output is 1 if both inputs are equal to 1. So here the output is 0 because one of the inputs is 0, the other one is 1. So my question is that if at time equal to t0, time equal to t0, t changes from 0 to 1. At which time output will change from 0 to 1. So does it happen immediately? If at T0 input changes, does the output immediately change? No. It takes some time for the input to propagate through the device and reaches to the output. There is a delay from the data to affect the output based on the input. Okay, it takes uh, some time. So we call this delay as a propagation delay. So if input at changes at t0 from 0 to 1, output will be changed from 0 to 1 at t0 plus t of propagation from low to high. It's a delay, so it's time. It's very small time, okay, but it takes some time. So if at time like five time second 5, okay, let's assume we have a counter and let's start the counter, and the counter counts from 0 second, 1 second, 2 seconds, 3 seconds, 4 seconds, and 5 seconds. At right at 5 seconds number 5, we change d from 0 to 1. The output will be changed from 1 to from 0 to 5 at 5 seconds point, for example 0001. Okay, so not exactly at 5. There is a delay to for the there is a delay for the data, for the input to change the output. Okay, so we call this propagation delay. Now here is a question. If we have a signal, if we have, let's say we have a D flip-flop, and it's a clock cycle, and here we have Q. First thing I'm going to discuss now is about the clock cycle. So far, we showed the clock cycle something like this. Yes, it is an ideal clock cycle. Ideal clock cycle changes from 0 to 1 and or 1 to 0 very sharp, very sharp. At like t equal to t0, the in like the clock value changes from 0 to 1 immediately, or from 1 to 0 immediately. But we know that in reality, in the practic we know that practically it takes some time for the clock to change from 0 to 1, or from 1 to 0. So if we zoom in this area, it is not like this. In fact, it is something like this. Okay? The same story for falling edge. It is not like this, very sharp. When it changes from 1 to 0, it is like this. It takes some time for the clock, or any signal, not just clock, any signal, to change from 0 to 1 or 1 to 0. So in like practically this one is not correct. We should show it like this. Okay, so here I'm going for this flip-flop. I want to show like a clock cycle in this way. So if we have a clock cycle which starts from 0 and changes to 1, and 1 to 0, 0 to 1, 1 to 0. So this one is a real clock cycle. And we have a D input. Okay, so a rising or falling edge, let's say, is like a middle point of these transitions. So like middle. Okay, so we have also Q, and D is 0 and Q is 0. we know that if D changes from 0 to 1, Q also changes from 0 to 1, because for D flip-flop, Q of T plus 1 is equal to D. Okay, so the question is that can we change D from 0 to 1 at this moment? Or can we do that? If we do that, does it ever like changes the output like this? The answer is no, we can't do that. There is two definitions called setup time and hold time. What is the setup time? Setup time says it is setup time is the minimum time, the minimum time, like the minimum time that the D signal must be stable prior to the positive edge of the clock signal. You know, the minimum time that the D signal must be stable prior to the positive edges of the clock signal. Positive edges for high active. If the flip-flop is low active, of course it's falling edge. So we have a time here. Let me just show it with different color. We have a time here which we call it TSU, T of setup or setup time. Setup time says in order for D to affect the output, the input D must be stable prior to the positive rising edge with the minimum time of TSU. So the input D must change from 0 to 1 no later than this time. If D changes from 0 to 1 later than this moment, so the distance, the time gap between like the positive edge and the change of the D will be less than setup time. So it's not gonna work. We get wrong output. So this one is T setup. Let me write the definition for setup time. So setup time or T of SU, the minimum time that the D signal must be stable prior to the positive edge or negative edge for falling edge sensitive. Okay, positive edge or negative of the clock signal is called the setup time or T of SU of the flip flop. So if we have an IC for flip flop, if we look to the data sheet of the IC, we will see the setup time for the IC. So Now one more thing. Let's go back to the after we activated the signal like at this moment, and now another question: how soon after the rising edge I can change my input? Because I know that if I change input from 0 to 1, as we see here, let's just complete the output. Here is the Q. The Q doesn't change like exactly the same time of the clock cycle. Why? Because we have propagation delay. So we should show the propagation delay. So we will have a little delay. So it comes a little like a little, it changes a little after the clock. Okay, and this time, of course, is T propagation low to high. Why don't we call it T propagation? Because T propagation delay might be different for like rising or falling. Okay, so for changing the signal for output from 0 to 1, we might have like one propagation delay, which is different than the propagation delay for like falling edge. Okay, so we have two propagation delay. We have propagation delay from low to high, and we have propagation delay from high to low. Both are different. They can be same, that's okay, but they can be also different. Okay, now that the output change, my question is that how soon after the clock cycle I can change my input from 1 to 0, because as we know the output of the D flip-flop, the Q, it's not gonna change until the next rising edge. Okay, until the next rising edge, which is here. So if we change the input at any of these moments, the output will be stay like 1, and it will be changed in the next rising edge. That's correct, because we know that the flip-flop changes its state once per clock. But still there is a question. Still the question is that soon after uh, how soon after like the positive edge of the clock we can remove the signal. Here we have something called hold time. So we had setup time, we have propagation delay, and we have something called hold time. What is hold time? Hold time is the minimum time that the D signal, the input, must remain stable after the positive edge of the clock signal. So for setup time, we say the minimum time that the D signal must be stable prior to the positive edge, but hold time says the minimum time that the D signal must be stable after the positive edge. So here the signal of like the signal of a D cannot be changed from 1 to 0, cannot be changed from 1 to 0 sooner than this time, which is called T of H, T hold. So the input has to be stable like at least TH after the positive edge of the signal. So we had three definitions. Propagation delay, it's the delay it takes that the effect of the input like be shown in the output. or the input propagates or moves through the input to the output. We have setup time, which is the minimum time that the signal must be stable prior to the edge, and hold time, which is the minimum time that the signal must be stable after the clock cycle. Okay, let me just write the definition of hold, T hold. So we have hold time, T sub H, the minimum time that the signal must remain stable after the positive edge or negative edge for falling edge sensitive of clock signal is called hold time, or T of H, of the flip flop. Okay, so it's very important to know these definitions. So the next time that I gave you like an example like this the flip-flop and ask you to complete what I want you to do, I want you consider. I don't want you show the signals like this. That's okay if you do that. That's fine. But the one thing that you are supposed to show is the propagation delay. So the Y input, Y output, I want you show the Y output like this. Okay, you see we have the propagation delay shown. Okay, a little shift to the right, a little delay, not change exactly at the edge, because we know that it's not gonna work. It takes some time for the input to change the output. Okay, so the next time or next examples we will consider these propagation delays. Okay, so now that we learned latches and flip-flops, it's time to build some more complicated uh, devices using this flip-flop. The first component and first device that I'm going to talk about is a register. Register is the most important part of a processor because it keeps the data inside the processor. A processor without a register is nothing. It's not gonna work. The register is memory for the processor. Okay, so we are going to talk about register. But what is a register? We know that one flip-flop can store 1 bit of information. If we use a set of n flip-flop, they can store n bit of data. So a set of n flip-flop is called a register. That's it. So it's very simple. If we know what is the flip-flop, the register is like the combination of n flip-flop. That's it. So let's write the definition of a register. We can say a flip-flop stores one bit of information. Okay. Then set of n flip-flops is used to store n bits of information such as n bit number we refer to these flip-flops as a register. You should notice that a common clock is used for each flip-flop in a register. So it says that if we have n bit register, a common clock signal is connected to all of those registers. So here we want to show a 3-bit register. So let's say 3-bit register. Okay, 3-bit register is consists of 3 flip-flops, D flip-flops. Okay, so D I0, information 0, information 1, and information 2 are connected to these 3D flip-flops, and output of these flip-flops are called A1, A0, A1, and A2, and all these flip-flops have a clock input and a common clock cycle. A clock is connected to these flip-flops. Okay, so by clicking the clock cycle, the inputs from I0, I1, and I2 will be moved to A1, A0, and A2. And of course, we need to have a clear input to clear the data stored in this register. So we have a clear input which is like this. Okay, so if the clear input goes to 0 from 1, the outputs of flip-flop will be set to 0. And we know how does the D flip-flop stores the data. So in order to store 1 bit of information in one D flip-flop, we apply the information in input D, like apply 1 clock cycle. The input moves to the output, so we stop applying more clock cycles, so the output will be always like constant. So the data at the input move to the output, and it will be stored at that location until the next like clock cycle we apply. So we don't have to apply or like the clock cycle continuously. We can apply 1 clock cycle and then disable the like the clock signal, So by applying one clock signal, the information moves from input to the output, and until the next clock cycle, the output is constant. Okay, so let me, for example, show you one thing here. Let's say we have a D flip-flop here, D flip-flop, and it's a clock cycle. There are different ways to store data in a D flip-flop. There are tons of different ways. One of them is like applying like the clock signal in this way. So it's a clock and right, signal right. Okay, so and here is data. So the clock cycle is like clicking continuously. We cannot stop the clock cycle from. So this one is a clock cycle. We have data, and let me just dash the light this signals, and data is 0 at this moment, changes to 1 at this moment, changes to 0, 0, 1, 0, 1, 0, 1, and this is the data, for example. Now we have a right signal as well. It is 0. As long as the right signal is equal to 0, there is no clock applied to the D flip-flop. So nothing moves from the input to the output. So output is always equal to 0. So if we say here is Q, Q always is 0. If a right signal is 0, Q is always 0. Okay, now let's say at this moment, okay, we want to write the data, or not to write the data, sorry, we want to store the data at this moment, not this moment, let's say at this moment we want to store the data. So what we do, the right signal will be activated before that clock signal, clock signal activated. Now what's happening at this moment? The right signal is 1, and the clock will be changed from 0 to 1. So the clock input of the flip-flop will be changed from 0 to 1. So the data will move from data signal to the output. So output will be changed to the 1. So now output is 1, and then we deactivated the the right signal, deactivate the right signal like this. In the next rising edge, not here, let me just, yes, we deactivate like this. Okay, in the next rising edge, because the right signal is 0, there is no clock signal applied to the D flip-flop. So as a result, this value of the data, it's not going to change the output. Why? Because a right signal is 0, and the clock signal entered clock signal to the flip-flop is equal to 0. So the output will remain 1. Okay? The same thing in the next clock cycle, the output is 1, and so on. So the output is always 1. So if we look to this timing diagram, we see that by activating the right signal at this moment, we store this data in the output, and the upcoming changes of the input doesn't change the output because the right signal is deactivated. So we can say that we stored this data, the like data D at this time. I'm trying just to erase these highlights. Just give me a second to erase these highlights. Okay, so we can say that we we stored this data in the flip-flop. Until when? Until the next activation of a right signal. Okay, so it's the way we can store data in one flip-flop. So if we have n flip-flop, they can store n bits of data, and it is called a register. Okay, so for a register, I0 moves to A0, I1 stores in A1, I2 in A2. Okay, so just there is no movement or shifting in this data. But we have one other device called shift register. Shift register. What is a shift register? It's like a register that provides the ability to shift its content. To shift its content. So like if A2, A1, A0 is 110, a shift register is able to shift it to the left like this, or shift it to the right like this. Shift the data, like move this one to here, this one to here, and a 0 will be entered here. It is called shift left, shift right, sorry. And or we can have this information and we can enter a 0 from here to here, here to here, 1 to here, and we call it shift left. Okay, so shift register is able to shift its content to the left or right. So let me write the definition. We can say a register that provides the ability to shift its contents is called a shift register. Some shift registers are able to shift the data to the right, some of them are able to shift data to the left, some of them are able to shift the data in both directions. So here we have a 4-bit shift register. For example, a 4-bit shift register is as follows. Okay. 4-bit shift register. So let's have 4 D flip-flops. 1, 2, another circle. It's like square. 1, 2, 3, and 4 flip-flops. And input D, output Q, input D, output Q, input D, output Q, input D, output Q, and we connect the inputs outputs in this way, and on the right we call it serial output, or SO. The left we call it serial input, or SI, and all of them are connected to a common clock signal. Clock. So which direction this flip-flop can shift, this register can shift the data? Of course, it's able to shift the data from left to the right, okay, from left to right, because the output of each flip-flop is connected to the input of the flip-flop at its right side. So the output of a given flip-flop here is connected to the D input of the flip-flop at its right, as I mentioned. All flip-flops receive common clock pulses also, which activates the shift of the data from one stage to the next stage. So each clock signal, let's say rising edge, each clock signal shifts like data one stage from left to the right. So if we call this a D flip-flop 1, 2, 3, 4, each rising edge transfers or shifts the data of flip-flop 1 to 2, 2 to 3, 3 to 4. The next clock again 1 to 2, 2 to 3, 3 to 4, and flip-flop 1 gets its input from serial input, and flip-flop 4 sends the data to the serial output. Okay, so let me just write it down for you. We can say the output of a given flip-flop is connected to the D input of the flip-flop at its right. All flip-flops receive common clock pulses which activate the shift of data from one stage to the next. Okay, so this flip-flop that we show here is able to shift the data only from left to right. So we can say this shift register is unidirectional, is unidirectional. In parentheses, we can say left to right. Each clock pulse shifts the contents of the register one bit position to the right. Okay, so this one is like a detailed explanation of how a shift register works. Okay, now I'm going to show you one example on shift register. So let's say example, suppose sequence of 0001101. I will explain this arrow goes to the 4-bit shift register. Shown above. So it is like left to right shift register. We want to find the output for 8 clock cycle. Initial state of all flip-flops is 0. Okay. So first thing I need to mention this arrow. It means that if these 8 bits are supposed to enter to like a shift register, this bit will enter first, this one second, this one third, this one fourth. So the bit enters to the shift register first is shown by the arrow. So in fact, the arrow shows the direction of the data that enters to the flip-flop. The same thing for the output. Okay, so these arrows show, like this arrow shows the direction of the data which applied to a device. Okay, so it says that for 8 clock cycles, so we need to have a table. Input, output, Q0, Q1, Q2, and Q3. And here is clock cycle. So clock cycle T0, T1, T2, rising edges, T3, T4, T5, T6, and T7. Okay, the input, we need to like copy this data in this column. Okay, so in which order? Of course, the right bit is enters first. So we say at T0 input is 1, T1 input is 0, T2 input is 1, T3 input is 1, T4 input is 1, T5 input is 0, T7 input is 0, T6 input is 0, and T7 input is 0. What about the outputs? At the beginning, before like first clock cycle, which is here, T0 is initial conditions. In fact, the initial conditions, we know that all of them are 0, like it was set here. So the initial conditions are 0. So T0 is initial conditions. So T uh, 1. What's happening in T1? The input moves to the Q0. Q0 moves to Q1. Q1 moves to Q2, and Q2 moves to Q3. The next state, next clock cycle, 0 moves to Q1. Q1 moves to Q2. Sorry, input moves to Q0, the Q0 moves to Q1, Q1 moves to Q2, Q2 moves to Q3. The next step, 1 moves to here, 1 0 1 0. The next one is 1 1 0 1. The next one is 0 1 1 0. The next one 0 0 1 1, and finally 0 0 0 1. And this one is like the output. So we see that all the inputs move to the outputs, and the same story for other stages as well. Okay, I try to show all of them. Okay, so what is the output sequence? Output sequence, of course, is the output of last flip-flop on the right, which is here. So the output, serial output is equal to 0 0 0 0 1 0 1 1, and we put this let's we put this arrow. Let's go for it. So it means that The first output, of course, is this zero, the second one, first one, second one, third one, and so on. Okay, so this one is a shift register, and the next device that we can uh, build by flip-flop and registers, which is very useful device and very critical component for electrical and computer engineers, is a counter. Counter can be built in so many different ways with different types of registers, flip-flops, T flip-flop, D flip-flop, JK flip-flop, and different methods. Okay, we have different types of counters. What is a counter? If I want to define a counter in a very computer engineering way or scientific method, I should say that the counter is a register that goes through a predetermined sequence of binary states. Predetermined sequence of binary states. So like 0 to 1, 1 to 2, 2 to 3. But one thing before we start discussion about the counter doesn't have to count in this order. The counter, we can design a counter that counts from 0 to 5, from 5 to 8, from 8 to 2, from 2 to 6, and from 6 to 0. And then 5, 8, 2, 6, 0, 5, 8, 2, 6, 0. This one is also a counter, okay? The counter is like goes through a predetermined sequence of states. Okay, those states like uh, can like those states uh, don't have to be in order. So like in digit orders. So they can be like 0, 5, 8, 2, 1, 6, 0, 5, 2. Okay, so let's see. Let's write the definition of a counter. I'm trying to erase this. I should change my tablet. Okay, so a counter is essentially a register that goes through a predetermined sequence of binary stages or states. Counters can be used in digital systems for many purposes. They may count the number of occurrences of certain or they can keep track of time, which is very important for us. We have, as I mentioned, different types of counters, but we have synchronous and asynchronous counters. We are interested in synchronous counters. The synchronous counters like work with clock pulses. Okay, we have also asynchronous counters that work based on the change of the inputs, not clock pulses. But we are interested in synchronous counters. Okay, so as I said, in synchronous counter, clock pulses are applied to the input of all flip-flops, and it is a common clock that triggers all the flip-flops simultaneously. So in synchronous counter, we have a common clock that triggers all flip-flops simultaneously. So we have a common. It's very interesting. I select the red color. It like it is black. I select black color. It shows the red color. So uh, a common clock triggers all flip-flops simultaneously. Okay. Uh, this flip-flop we want to learn at this moment is a not flip-flop counter. Is a synchronous counter with T flip-flop, toggle flip-flop. What is T flip-flop? We know that the T flip-flop changes the output if the input is 1. Complement the output as long as the input is 1. So now I'm going to show you how to design a synchronous counter with T flip-flop. Okay, so first let's see the characteristic table or the cycles we're looking for. So uh, we will have clock cycle, clock cycles, and here we want to count from 0 to 8. So we will have Q2, Q1, Q0. So count from 0 to 7. How many like numbers? It's 8 numbers, which is 2 to the power of 3. So how many bits do we need to show 8 like different combination? We need 3 bits. So we need 3 flip-flops. Okay, so uh, clock cycle 0, 1, 2, 3, 4, 5, 6, 7, 8. At initial point we want to have Q2, Q1, Q0 equal to 0. So for 1, we have 0, 0, 1. For 2, we have 0, 1, 0. For 3, we have 0, 1, 1. For 4, we have 1, 0, 0. 5 is 1, 0, 1. 6 is 1, 1, 0. 7 is 1, 1, 1. And 8, of course, is like more than 3 bits. It's 4 bits. But these 3 bits for number 8 are 0 because 8 is 1, 0, 0, 0. So we see that these 3 bits are 0. So we want to design this counter by T flip-flop. Okay, so what we need to do? First, let's look to Q0. If we look to Q0, we see that Q0 changes on each clock cycle. Q0 changes on each clock cycle. So let's write it down. Q0 changes on each clock cycle. Okay. Let's look to Q1. Q1 changes only when Q0 is 1. So you see Q0 is 1, Q1 changes. 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 Okay, so let's just take a note. Q1 changes only when Q0 is 1. Okay, let's look to Q2. Q2, if we look to Q2, we see that Q2 changes only when Q0 and Q1 both are 1. You see? So Q2 changes when Q1 and Q0 are both equal to 1. So we can say Q2 changes only when Q0 is equal to Q1 is equal to Q is equal to 1. So if it was 4-bit counter, we could say Q3 changes only when Q0 is equal to Q1 is equal to Q2 is equal to 1. Qn n-bit counter changes when Q0 is equal to Q1 is equal to up to Qn is equal to 1. Okay, so this one is a general like conditions for a counter with T flip-flop. Okay, so it's up counters, so like don't forget this one is up counters because it counts for like upward. Okay, so we want to design it. We know that the T flip-flop changes the output when like the input is 1. So because okay, so now for this example, let's focus on 3-bit flip-flop. So we will have 3 T flip-flop. So T0, the input of the first flip-flop. I'm talking about this flip-flop. T0 has to be 1. Why? Because Q0 changes on each clock cycle. Remember the characteristic table of T flip-flop. If T is 0, q of t plus 1 is q of t. If t is 1, q of t plus 1 is qt bar. Okay, so because the q0 changes on each clock cycle, t has to be equal to 1. So t0 is equal to 1. What about t1? T1 changes when q0 is equal to q when q0 is equal to 1. So t1 is equal to q0. What about t2? T2 changes when q0 and q1 both are equal to 1. So q1, q0 both should be 1. If we continue this, we will have, of course, t3 is equal to q2, q1, q0. And if we continue up to tn, we can say tn is equal to q of n minus 1 up to q1, q0. But as I mentioned before, in this example, we focus on 2 bits. So if we now it's time to design the circuit. So the design of the circuit by having this information is very easy. We have 3 T flip-flops. T0, T1, and T2. Okay, so T1 is 1, is connected to 1. Not T1, sorry, T0 is connected to 1. T1 is connected to Q0. T2 is connected to Q1, Q0. So we get Q1 here. Like this. And Q2 is here. And of course, all of them have a common clock signal. Okay. Here is the clock signal. And don't forget the clear input, because we want to be able to reset the counter. This one is 3-bit counter with T flip-flop. What about a 4-bit flip-flop? 4-bit counter. If we show a 4-bit counter, we will have, so example, 4-bit up counter using T flip-flop. We want to design this. So we use 4 T flip-flops. Okay, and we have T0, T1, T2, T3. Here is Q3, which is output. T1 is connected to Q0. T2 is connected to Q1 and Q0. T2 is connected to Q2, Q1, and Q0. And that's it. the clock cycle clock input here is 1, and of course clear signal. This one is 4-bit counter. Don't forget that for this part, for T3, we know that T3 is Q2, Q1, Q0. So instead of like using 3 input AND gate like this, Q0, Q1, Q2, what we did, we already had Q0 and Q1 in the previous stage, and so we used two input AND gate to generate Q2, Q1, Q0. Okay, both these two designs are same. Okay, and if we show the timing diagram of this 4-bit counter, we will have this timing diagram. Let me just show you a timing diagram for counter. So the clock. Okay, so we have Q0, Q1, Q2, and Q3. Let's just mark the rising edges. Here we don't want to forget the propagation delay, so we apply propagation delay. Q0, all the like stages, all the outputs are in stage 0, so all of them are in a stage 0. We know that Q0 changes at every clock with a small delay of propagation. So this one is Q0. Okay. Now, what about Q1? Q1 changes every time that Q0 is 1. Again, we have a little more propagation delay. So every time that Q0 changes from 1 to 0, Q1 changes. So no, sorry. Every time at any clock, that Q0 is 1, Q1 will be changed. So the clock cycle 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, let's look. At clock cycle 1, we see that in rising edge, Q0 is 0, so Q1 also is 0. At clock cycle 2, at the rising edge of clock cycle 2 here, that I'm showing with this arrow, we see that the Q0 is 1, so Q1 will be changed. Okay, at clock cycle 3, Q0 is 0, so Q1 is not gonna change. Clock cycle 4, at this moment, Q0 is 1, so the Q1 changes. Clock cycle 5, Q0 is 0, no change. Clock cycle 6, Q0 is 1, change. Clock cycle 7, Q0 is 0, no change. Clock cycle 8, Q0 is 1, so we will have change. Clock cycle 9, Q0 is 0, no change. Clock cycle 10, Q0 is 1, we have change. Clock cycle 11, Q0 is 0, no change. Clock cycle 12, Q0 is 1, we have the change. Okay, so we complete the Q1. Q2 changes at any clock that both Q1 and Q0 are 1. So at which clock cycles both Q1 and Q0 are 1? Of course, here and here and here. Okay, so we start from 0, we continue until here, we change it to 0 and change it to 1. So you see that without like propagation delay, this circuit won't work. Because of this propagation delays, we can exactly zoom in and see that at the rising edge of Q4, rising edge of cycle 4, the Q0 is 1. If there was no propagation delay, Q0 would be something like this, and we had no idea at the rising edge the value of Q0 is 1 or 0, because it changed right exactly at that moment. So we had no clue that if the Q0 is 1 or 0. So propagation delay is very useful like delay for electrical circuits and components. And finally, for Q2 changes if all Q1, Q2, and Q0 all are 1. So let's see which moment all of them are 1. Of course, here. Okay, you see all of them are 1. So we can say Q3 is 0 until this moment, and at this moment will be 1. And this one is like timing diagram for a counter using the flip-flop. Okay, that's enough for today, and see you in the next lecture.